And welcome back to the second half of webinar unit 28. And we're discussing multi-degree of freedom systems for shock response spectrum. And we've already gone over the theory, the equations in part 1, and now for part 2 we're going to look at an example. So here's our 2-degree of freedom system, and sometimes people refer to this particular diagram as representing two-stage isolation. We could also think of it as if mass 2 were an avionics component and it was mounted to a base plate, mass 1, and then with the two springs there. So the first mass is going to be 5 pounds, and then the top mass is going to be, M2 is going to be 5 pounds. The bottom mass for the base plate M1 is going to be 2 pounds. The stiffness values we're going to choose to be the same, and each is going to be 4.6 times 10 to the 4th pounds force per inch. And the damping is going to be Q is equal to 10. That's actually the amplification factor. That will be for both modes, and that's equivalent to 5% damping. And we're going to actually do a series of analyses here. We're going to first do a normal modes analysis where we find those eigenvalues and eigenvectors. Then we're also, just sort of as an aside, we're going to take a look at the transmissibilities of those two degrees of freedom as well. So let's go to our MATLAB GUI here for our vibration data GUI package. So this week we're up to version 6.3. And I've kind of been working on a section called structural dynamics here. So let's click on that. It's under miscellaneous. Let's go to spring mass systems. And this is divided up into two halves. The left half here is for single degree of freedom systems. Then the right half here, or I should say the right side, is multi-degree of freedom systems. And let's go right to 2-degree of freedom system base excitation. So this will be an MDOF, which is a multi-degree of freedom analysis. Now we have two systems to choose from, and today we're going to do the system on the left. They're both 2-degree of freedom systems, but we'll choose the one on the left. And we're going to do English units, and at this point we're just going to type in the values from the PowerPoint slide. So I'm going to go ahead and do that, and then just Control-C, Control-V there. So before we do anything else, we need to calculate what the natural frequencies are. So let's do that calculation, and the output is written to the MATLAB command window. So get a couple of things we need to take a look at here. The first natural frequency, I'm just going to round these off, is 200 hertz. Then the second one is 700 hertz. Those are for the two modes. And then we can take a look at the participation factors and the corresponding effective modal mass values. So for mode 1, the participation factor is 0.13. For mode 2, 0.03. So the participation factor is 4 times greater for mode 1. And that means that the fundamental mode, mode 1, is more excitable than is the second mode. And then we have a similar situation with the effective modal mass values, where mode 1 has a higher value than mode 2. Now if we and actually the ratios between those pairs change, but let's not worry about that for now. Now let's take this modal sum value here, which is 0.018, and let's multiply that by 386, because these mass units here, these are really pounds force seconds squared per inch. So to get back to LBM, pounds mass, we multiply by 386, and we see that's almost equal to 7. Well, 7 is equal to 5 pounds plus 2 pounds. So we're accounting for basically 100% of our modal mass. And then you can see how the effective modal mass values are distributed. And then we have our mass matrix, and this happens to be in units of pounds force seconds squared per inch. So diagonal mass matrix, symmetric. Stiffness matrix. Stiffness matrix is fully populated, but it's still symmetric. You can see the stiffness values there. That's pounds force per inch. And then we have these mode shapes, and these are the mass normalized mode shapes. So let's look at mode shape 1. So the first, and these are in column format. So this is 4.96 and 8.29. So we could make a ratio between those, and I'm just going to be a little lazy and simplify, and I'm going to say that that ratio is almost a value of 2. So that means that as this base is being excited, and we're exciting mode 1, or excuse me, the base is supplying the excitation, and we're looking at the mode 1 response, that the second mass is going to be vibrating almost twice as much amplitude as is the lowest mass. We also notice that they're both effectively positive signs out here. That means the two masses are vibrating in phase with one another. Now we get to the second mode, and we have 13 and minus 2. So you see a change of sign there. That means the two masses are going to vibrate 180 degrees out of phase with one another. And it turns out that, I guess if we make a ratio of it, it's about ratio of 4 between those numbers, that this bottom mass is going to be vibrating with an amplitude about 4 times greater than that of the top mass. So that's just some information that we're extracting from the mode shapes. Okay, now once we've done our modal analysis, our normal modes analysis, we can enter in our damping. And we're going to have uniform Q is equal to 10, which is going to be 5% damping. So 5% damping or amplification factor Q is equal to 10 for both of the two modes. So we save that. Now after we've saved that, we see several other buttons have become visible. So there's all sorts of other types of analyses we can do. And let's go ahead to transmissibility frequency response function, or FRF. And we're going to plot this from 10 to 10,000 hertz. And these are transmissibility plots for the base excitation. Okay, so we get two plots here. Plot 1 is the acceleration transmissibility. So it says trans G divided by G. This means the numerator G corresponds to either mass 1 or mass 2, depending on the color. And the denominator G is the G level for the base excitation. Then we have versus frequency in hertz. So we have these two spectral peaks are the mode at 200 hertz. Then these two spectral peaks here are the mode at 700 hertz. Now, do you remember for the case of single degree of freedom spring mass systems, where the transmissibility at resonance would equal to the Q value? Well, we've got Q is equal to 10, and it looks like for mass 2 that might be really about 11 or 12. And then for mass 1, it's just about whatever that comes out to be, about 6 or so. So that neat and tidy way of picking off the Q value from the peak response at resonance no longer applies because we have a 2 degree of freedom system. Or I should say because we have a multi-degree of freedom system more broadly. But do you remember that half-power bandwidth method? If we were to take the half-power bandwidth method on either of those two peaks, that should come out to be 5% damping, which corresponds to Q is equal to 10. And then you can see for this second mode here, both of those peaks fall short of the 10 value. But they both correspond to Q is equal to 10, or 5% damping. And again, the way to verify that is to do that half-power bandwidth method, which we've done in previous units. So that's the acceleration transmissibility, and this is saying that if we excite the base, primarily it's the first mode that's going to be excited. But we do get some participation from the second mode as well. Now if we go to relative displacement, so this is transmissibility in inches divided by G. So this inches would refer to the relative displacement of either mass 1 or mass 2. Then the G in the denominator refers to the base acceleration G. So again, we have a pair of spectral peaks at 200 hertz, the first mode. And at least for mass 1, we have a spectral peak here at 700 hertz. And The situation's a little more ambiguous here with mass 2. It looks like there's some kind of a little jump thing going on, so I'm not really sure we could call that a spectral peak at all. And why that happens and how that happens, I'm going to have to assign myself an action item to explain that to you later. But one of the things we notice here for these relative displacement transmissibilities is that pretty much it's the first mode. The first mode is going to dominate the response for each of the two masses for relative displacement. And the participation from the second mode is going to be kind of marginal. So that's the transmissibility plots. Now, I have not shown you yet the underlying equations, and I probably need to go back and do that, but let's save that for an upcoming webinar. Okay, so we just sort of took a side trip and looked at the transmissibility ratios. Okay, then this shows you how to put those values into the GUI software that we just ran. And then we've already seen these. These are the normal mode results. Then we entered in the damping in the GUI package. We did the transmissibility analysis, and you've already seen this plot here, and you've already seen this relative displacement transmissibility as well, where the relative displacement response is dominated by the first mode. Okay, now we're going to have some fun, and we're going to do an SRS analysis. So I'm going to take these points here, these coordinate points, and do a Control-C, and I'm going to go to the command window here and do a Control-V. So now I have a file in the MATLAB workspace called SRS Spec. So we have SRS Q is equal to 10. We have natural frequency in Hertz and peak acceleration in G. And this particular shock, it could represent, say, a far field shock level, or it could represent a near field shock level for some less severe device, say a clamp band with bolt cutters. And typically these would start at 100 Hertz, but I'm taking this all the way down to 10 Hertz because I want to control the energy below 100 Hertz. And this ramp is actually just going to be a constant velocity ramp at 6 dB per octave, and then that transitions to a plateau. So we have two different ways of doing this. We're going to do first a modal transient analysis. And to do this, we need to synthesize a time history to satisfy this SRS, which actually I've already done, and that file is available on the blog. Then method 2, we're going to do the SRS approximation methods, and that will be the ABSUB method and the SRSS method. So here's our synthesized time history that's already available to us, and here's the file name for it, SRS 2000G _excel.txt. And this plausibly resembles a pyrotechnic shock. Now, there's no exact criteria or rules for saying what is and what is not a pyrotechnic shock, but with a little bit of imagination, that could represent a pyrotechnic shock. So what are we going to do next? Let's go to our vibration data GUI, and actually we want to go back to this 2_DOF_base_A where we've already been before, and let's do an arbitrary pulse. So we're going to use the digital recursive filtering relationship for applied force. And this is a response to arbitrary base input. The input array must have two columns, time in seconds, acceleration in G. So we have an external ASCII file, and it's that 2000G synthesized waveform. And once we've called that in, we can just go ahead and do our calculation. Get a whole series of plots, and I think there's going to be something on the command window as well. So let's see, let's just take a look at our accelerations here. What we have here is a combination of things. So on the left we have mass 1, that's the lower of the two masses, or you could call that the base plate. Then we have the acceleration response for mass 2, which we could say is the avionics component. And these are actually to different scales, so it looks like the the mass 1 is getting a higher response level than is mass 2. So that's part of the benefit of that two-stage isolation. And the response of mass 1, this sort of reverberation out here is at the 200 hertz. And we could verify that by counting the number of peaks and divide by time. Now also kind of superimposed here, it's a little harder to pick out. There is some 700 hertz response for the second mode. But there's also just some of that base excitation energy that sort of is propagating through to the response of mass 1. So we have really three different things going on here superimposed. We have some of that base excitation energy, as well as the modal response at 700 hertz, but more particularly at 200 hertz. Now when we get to mass 2, it looks like the response is almost exclusively the 200 hertz mode. There is a little bit maybe of 700 hertz going on there, as well as some of that base excitation that propagated through. But for the most part, that's the 200 hertz response there that you're seeing from the fundamental mode. Okay, we can also look at a couple other things here. We've got the relative displacements. Excuse me, these are the two accelerations for each of the two masses superimposed. So you can see sort of initially there's a little bit of a difference there, but then later on they kind of settle into the same pattern where they're vibrating in phase at 200 hertz. Then we could also take a look at the various relative displacement plots, and that could be useful for evaluating the spring deflections, or if we had isolators, making sure the isolators could withstand that deflection. Or there are ways of taking a relative displacement and converting that to force or stress or strain. And we're going to save that for a future webinar. And then here's just the base input. Of course, you've seen that before. It's in the PowerPoint slide. The next thing we could do, we're not actually going to do it now, but we could go through and save those acceleration time histories or the relative displacement time histories for use in other calculations. I'll skip over that for now, but just realize that that feature is available. And then the last thing we want to do here is we want to take a look at what's going on with the peak responses. So we have mass 1 and mass 2, and you can see their peak responses both for the positive and negative. So you can see mass 2 has less response than mass 1, and that's the benefit of the two-stage isolation. And then you can also see the corresponding relative displacements. And these two relative displacements are with respect to the base. Then we also have a relative displacement between the two masses, or more properly between the 2 degrees of freedom. So just imagine taking these values here and just copying and paste and going into a WordPad here, paste them into WordPad. And let's just set these aside for now, and we're going to come back to them in a couple of minutes. Okay, the other thing we can do here is we can do this SRS Per Approximation method. Now, to make this SRS Per Approximation work, it's really helpful that both modes have the same Q value, and that Q value is the same as the spec's Q value. And we really need to have all that correlation in place in order to make this approximation work out good. On the other hand, when we were doing that whole synthesis process, it actually was not important that both modes had the same damping. And it was also not important that the damping value for either of the two modes was the same as the spec. So the fact that the spec is Q is equal to 10, that's just an indirect way of working back to what the base excitation is. But once we know what the base excitation is, or at least we've synthesized a plausible representation for it, then we can apply that to any system whatsoever with whatever Q values it may have. So the whole method of going through the synthesis and doing the arbitrary pulse response using the digital recursive filtering relationship is actually much more flexible than what we're going to do now. But let's go here to this approximation method, and we need to apply the specification, which is natural frequency in hertz, and SRS in Gs. And that's actually, we did this earlier. That's SRS underscore spec. Remember, I copied and pasted the points into MATLAB. In fact, in case you're wondering, well, how did we do that? That was somewhere. Okay, that was this step right here. We just these are so simple. I don't bother to post files on my blog because you can just copy. You can just type those in yourselves. Okay, let's go ahead and do the calculation here. And we see a plot. This is just the specification. So SRS, Q is equal to 10. We've got peak acceleration in G. Got the natural frequency in hertz. Now, it just so happens by coincidence the G levels are going to be numerically equal to the natural frequencies along this ramp. That's partly because it's a 6 dB per octave. But what this SRS approximation method does is it says, okay, we've got a 200 hertz mode. Okay, that's 200 G, so let's retain that pair of coordinates. Then we've got a 700 hertz mode, and that corresponds to 700 G, so let's keep that pair of coordinates. So we've got two pair of coordinates. And once we have those two pair of coordinates identified, we throw away the SRS curve. Now, what we just did was for acceleration. If we can take those two acceleration points, convert them to relative displacement by dividing by omega sub n squared. And I've already told you in previous units how to go from absolute acceleration to relative displacement, so you should already remember that. Okay, so let's go to the command window and see the results here. So we've got, let's see, for degree of freedom 1 or mass 1, or degree of freedom 2 or mass 2, we've got the square root of the sum of the squares, peak acceleration, peak absolute G levels. Then we have the absum method. Now the absum method, again, this assumes that the peaks for each of the two modes happen simultaneously, and that applies to both of the degrees of freedom. So the absum should really be regarded as the upper limit. And then not shock response spectrum, it's the square root of the sum of the squares method. You can see for degree of freedom 1, it's about 25% less, and then there's also a difference between going from absum to SRS. Not a 25% drop, I don't think, but you can figure out the percent drop yourself. Okay, so there is some spread there between the two methods. When we get to relative displacement in inches and we look at each degree of freedom or each mass response, we look at the two methods side by side, we can see that the difference becomes more narrow. And in fact, once we get to degree of freedom 2, those are almost the same numbers for our purposes. And the reason is that for relative displacement, this is primarily just a single mode response. Whereas for acceleration G, it's somewhat of a blend of each of the two modes, modal responses, although with the fundamental mode dominating. But nevertheless, a mixture of the two, a better mixture of the two modal frequencies and modal responses at those frequencies. So the next thing we're going to do is take these numbers here and take our modal transient results, and let's put those all together in one table here so we can get a good idea of what's going on. So back to the PowerPoint slides, and I think I've just got some things you've seen before here. So this was our synthesized pulse. Oh, I should have showed this to you. Better late than never. Shock response spectrum, Q is equal to 10. Peak acceleration G, natural frequency in hertz. This is the SRS of our synthesized time history, which we've already used. And you can see it's pretty close to the nominal specification across all natural frequencies. And then we have the plus and minus 3 dB tolerance bands. So the positive and negative are well within the plus and minus 3 dB tolerance bands for that pulse. So this pulse was good to go for the base excitation, which we've already run at this point. Okay, so these slides here, you can just kind of go through the PowerPoint slides yourself, just kind of go through the steps of what we just did. So this at this point is just a review. There's the acceleration for mass 1, acceleration for mass 2, and then we did this simplified SRS approximation method for multi-degree of freedom systems. Okay, so here's what we really want to look at. This is going to be a summary. We're going to look at two tables. The first is peak acceleration. There is a row for each of the two masses, or if you want to say for each of the 2 degrees of freedom. So for the absum value here, it's about 404 G, and then 309 for the SRSS method. And the modal transient value just kind of falls in between, kind of midway between those two values. So this is kind of showing us that we have good ballpark agreement. So that kind of gives us some ways to cross-check the methods with one another. And I guess if we want to be conservative, we'd say, okay, we're just going to use the absum value here, if you can tolerate that conservatism. And then we have a somewhat similar story here for mass 2. The acceleration values decrease for each of the 3 methods, but again, the modal transient is kind of midway between the SRSS and the absum methods. So that kind of gives us some measure of confidence in everything we've done here. And again, for acceleration, although the response is primarily the fundamental response, the responses are a blend or mixture of the 2 modes to some extent, with the second mode making less of a contribution. Okay, now here's the same data all over again, except we're looking at peak relative displacement in inches. And in this case, the values are going to be more closely spaced because we have primarily it's just the fundamental mode that's dominating the response. Again, absum is always higher than SRSS method, but just with a narrow gap. Now, in this case here, the modal transient for mass 1 was slightly lower than the SRSS method, and the modal transient for mass 2 was just slightly higher than the absum method. And I'm not going to really worry about that. It could just sort of be that we need some numerical thing going on, or we need to realize that the synthesized SRS was not exact. There was some variance there about the nominal line. In fact, if we go back and see how well did we do at 200 hertz and 800 hertz. Well, at 200 hertz, those 2 curves are pretty close to nominal, but not exactly equal to. And then at 700 hertz here, looks like both positive and negative were slightly higher. So who knows? It could just be some imperfection in our synthesis, or some significant digit thing, or some numerical thing of some sort. And you know, I'm just not going to worry about that, because those values are for shock and vibration analysis purposes. Those values are very close to one another. So again, I guess if we want to be conservative, we'd go with the absum values. Although in this case, the modal transient was 1/1000th of an inch higher, which is just a trivial difference. So just to sort of summarize, let me go back to the very first slide we took a look at here when we did part 1, or actually the second slide. We do have 2 options, and I really like the modal transient analysis because it's fun to do numerical experiments. One of the drawbacks, though, is say you have a finite element model with 10,000 degrees of freedom or 100,000 degrees of freedom. Well, this modal transient analysis can take a long time. We can somewhat shorten the time and the memory space by just limiting the response outputs at a handful of carefully selected degrees of freedom, and I've done that before too. But as much as possible, that's my choice as method 1. But if we want something that's just quick and simple, we can use this method, these approximation techniques like the absum method, that use the participation factor and normal mode results. And those are good just for kind of a quick calculation or a quick estimate. But obviously, the more tools we have in our toolbox, the better off we are. And there's some things I need to do. I want to go back and, well, let me back up a little bit. If we have a modal transient analysis results, it's very easy to post-process the data, or reasonably easy to post-process the data for stress and strain. For the approximation technique with the multi-degree freedom SRS estimates, I don't have a method to show you today for taking those values and converting them to stress and strain. I've got an idea in my mind how to do that, but that's going to be another webinar, and there'll be concerns about some accuracies. We'll have to make some conservative assumptions, but I think if we work through what's called the pseudo velocity, we can get to that point. So maybe for our next webinar, we should go back and talk about the pseudo velocity stress relationship. So anyways, thanks for participating, and please do this as a homework exercise, this example, or make up one of your own. And if you have any questions, send me an email. So goodbye for now. Thank you.